An 8-kilometer error changed Earth's rotation speed. On July 17th, 709 years before the Common Era, the sky darkened over the ancient Chinese city of Chufu. Chroniclers recorded a total solar eclipse, and this account stands as the earliest precisely documented event in human history. Nearly 3,000 years later, astrophysicists used this record to calculate how the moon slows our planet's spin. But where did the moon itself come from? Was it born from a colossal impact? Or is that just an elegant theory lacking solid proof? Meanwhile, a strange gamma-ray signal emerges from the heart of the galaxy. Is it a trace of dark matter, or just another ghost in the data? The chronicle was called the Spring and Autumn Annals. It was compiled in the 5th century before the Common Era. 37 solar eclipses, observed between 722 and 481 years before the Common Era, are recorded in it with unsettling precision. Each eclipse serves as a data point. Each data point helps scientists check how fast the Earth's rotation has slowed over thousands of years. This slowing isn't constant. It generally decreases due to tidal interactions with the moon. The moon pulls on the oceans, and the oceans, in turn, drag on the planet. Slowly, but relentlessly. Ancient eclipse records are the only tool we have to calibrate models of this slowdown over time spans no modern instrument can cover. Yet here lies a problem that went unnoticed for decades. A new study published in the astrophysical journal Letters revisited an eclipse from the year 709 and asked a simple question. Exactly where was it observed from? Earlier calculations relied on specific coordinates in Khufu, but archaeological evidence told a different story. The actual observation point lay about 5 miles away from the previously used location. 5 miles, that's just a short walk in a city. Yet for models of the planet's rotation, this shift changes the calculated position of the sun at the moment of the eclipse. That, in turn, adjusts the entire curve measuring Earth's slowing rotation. Put simply, by pinpointing where the observer stood nearly 3,000 years ago, scientists had to recalculate how fast Earth was spinning in the time between then and now. Let's pause for a moment. Bamboo strips. Ink. The hand of a scribe, carefully drawing characters by the glow of an oil lamp. This person had no idea they were recording data for orbital mechanics. They were writing a sign, and today we read it as braking parameters. Between these two readings, 27 centuries and a completely different worldview, yet the line remains the same. There's another detail connected to the same eclipse. In the Book of Han, written about 700 years after the event, a curious phrase appears. The sun was yellow on the top and the bottom. Some researchers interpret this as a description of the solar corona, that glowing halo visible only during a total eclipse. If that's true, it would rank among the earliest recorded observations of the corona in history. But, and this is important, 7 centuries separate the event from the text. The account is considered unreliable. That yellow glow might have been the corona, or it could have been a literary flourish added over generations. Here, a pattern starts to emerge, one that will repeat itself over and over. Let's call it the clue without a witness. You have an indirect trace, a recording, a signal, an anomaly in the data. Then, there's an event that could explain that trace, but no one saw it directly. Time or space stretches between the trace and the event like a vast chasm. The only way to bridge it is with a model built on other, equally indirect clues. Remember this pattern. The moon slows down the Earth. We know this from ancient eclipses. But who created the moon itself? A body weighing 73 quintillion tons that drifts away from us by nearly 0.4 of a centimeter every year. How does a rocky planet end up with a satellite that, by mass ratio, feels more like a partner than a captive? The answer might not lie out in orbit, but much deeper, beneath our feet, down in the mantle, where seismic waves behave as if they're running into something alien. 4.5 billion years ago, there wasn't a single planet here. Just fragments, scorching chunks of rock and metal spinning around the young sun in a dense disk, where temperatures at the inner edge soared to 2,000 degrees. These pieces collided. They stuck together. then shattered apart, and collided again. These weren't rare accidents. This was the only way to grow. The early solar system behaved like an enormous billiard table, with balls shooting off in every direction at once. The rules were simple. Those who gained mass pulled in neighbors, while those who didn't became part of someone else's mantle. Planet-sized collisions weren't disasters. They were routine, just a normal Thursday. Here's what's fascinating. That era came to an end. The system settled down. The planets drifted into their orbits and stopped crashing into each other. But the scars remain. All 4 inner rocky planets carry marks that defy explanation, except for impacts of unimaginable force. Let's lay out the clues. Mercury, the smallest planet in the solar system, yet it has an unusually massive iron core. That core takes up about 85% of the planet's radius. Imagine a peach with a pit as big as the entire fruit and only a thin layer of flesh around it. One explanation goes like this. Mercury was once larger, with a normal thick mantle. Then, a colossal impact stripped that mantle away like peeling skin. What's left is the core, wrapped in a thin, rocky shell. Venus, the only planet in our solar system that spins the opposite way. While all the others rotate counterclockwise when viewed from above the North Pole, Venus turns clockwise. It moves slowly, almost reluctantly, as if it had been forced to flip over. And maybe that's exactly what happened. A collision so powerful, it knocked the planet's axis off balance, reversing its rotation. Mars makes this even clearer. Its northern hemisphere is smooth lowlands. The southern hemisphere is rugged highlands, riddled with craters, standing 3 to 5 kilometers higher. The boundary between these 2 zones cuts sharply, almost like it was drawn with a ruler. This division is one of the oldest mysteries in Martian geology. It's also one of the simplest to explain. If you imagine a Pluto-sized object smashing into the northern hemisphere early in the planet's history. 3 planets, 3 distinct scars, a stripped mantle, a tilted axis, a fractured surface. Each tells its own story, but together they paint a bigger picture. The early solar system was a place where planets took shape through destruction. Massive collisions weren't exceptions, they were the rule. And if this rule applied to Mercury, Venus, and Mars, it would be strange if Earth had escaped unscathed. It didn't. The leading theory about the moon's formation is clear. About 4.5 billion years ago, a Mars-sized planet slammed into the young Earth. Scientists call it Theia, named after the mother of Selene in Greek mythology. The impact hit at an angle. Some of the debris was thrown into orbit and came together to form the moon. Part of Theia vaporized, scattered, and mixed with Earth's rock. But what happened to the rest? Deep beneath the surface, at the boundary between the mantle and the core, about 2,900 kilometers down, seismic waves from earthquakes behave strangely. They slow down, not just a little, but noticeably, by several percent. It's as if they're traveling through something denser and hotter than anything around them. There are 2 of these zones. One lies beneath Africa, the other beneath the Pacific Ocean. Each is the size of a continent. More precisely, each covers an area comparable to the combined size of Australia, India, and Antarctica. And they don't resemble anything else in the mantle. Scientists call them large, low-shear velocity provinces. Researchers discovered them using data from global seismic networks. Thousands of seismographs worldwide have recorded, over decades, how earthquake waves distort as they pass through these regions. Let's be honest. Deep inside our planet, far beyond the reach of any drill, lie 2 structures as vast as continents. They're the densest things around, and you can't help but wonder, where did they come from? One theory answers this with unsettling clarity. This is Theia, or rather what remains of it. Fragments of an alien world that, after crashing into Earth, sank into its molten interior and, over billions of years, settled near the core. They didn't dissolve. They didn't blend in. They just sit there, 2 massive pieces of another planet, trapped forever inside our own. The Earth beneath our feet might not be a single planet at all. It could be 2, merged so long ago that the seams are visible only to instruments. But here's the question: how much can we trust the signals coming from such unimaginable depths? And could their source be something completely different? The year was 2018. The European spacecraft Mars Express, which had been orbiting Mars for 15 years by then, sent data back to Earth that literally took planetary scientists' breath away. The Mars Advanced Radar for Subsurface and Ionosphere Sounding, or MARSIS, is an instrument that can scan beneath the Martian surface using radio waves, much like an X-ray reveals bones. It detected an unusually bright reflection beneath a 1.5 kilometer thick layer of ice at Mars's south pole. So bright, in fact, that it seemed to have only one explanation. Beneath that frozen shell of carbon dioxide and water ice, there was a lake. Liquid, briny water. Right now. Not billions of years ago, not just in theory, but now. Headlines exploded within hours. A lake on Mars, liquid water, a possible habitat for life. The discovery was published in one of the most respected scientific journals. Everything looked flawless: the data, the modeling, the interpretation. A compelling hypothesis backed by a striking radar signal. And this is where the story takes a turn that the headlines missed. NASA operated its own spacecraft in Mars orbit, the Mars Reconnaissance Orbiter. On board, it carried a radar called SHARAD, a different kind of instrument but designed to explore the same region. The SHARAD team aimed their antenna at the South Pole, once, twice, 3 times. Multiple passes over the exact spot where the European radar had spotted a bright patch. The result? Silence. No similar signal. Where the European radar shouted, "water," the American radar heard nothing unusual. 2 instruments, 1 region, opposite results. This isn't a minor discrepancy, it's a crack right in the foundation of the discovery. But before dismissing the hypothesis, the Mars Reconnaissance Orbiter team decided to make sure the problem wasn't with their own spacecraft. The SHARAD radar was mounted in such a way that, with the orbiter's standard orientation, its body partially blocked the antenna. In other words, the spacecraft was interfering with its own instrument's ability to listen. To get a clean, undistorted signal, they had to rotate the 3-ton structure in the void of space by a full 120 degrees. Not just a slight course correction, but literally flip the orbital probe so the antenna faced completely open toward the surface. Every maneuver burned precious fuel, which only had a few years' worth remaining. Every turn posed a risk to equipment that had already operated in space for over a decade. The engineers agreed. Slowly, degree by degree, the spacecraft rotated in the darkness above the Martian pole. The signal grew stronger. Much stronger, the body's shielding really had been muffling the data. But SHARAD still didn't detect that bright patch beneath the ice, the very one thought to be a lake. Not even with its perfectly positioned antenna. Not even with the clearest possible signal. The idea of an underground lake suddenly seemed much less likely. Not because anyone chose to doubt it, but because a second, independent instrument operating under the best conditions failed to confirm it. So what did the MARSIS instrument actually see? What created that bright spot that fit so perfectly into the picture of a hidden underground sea? One leading alternative hypothesis says the signal has nothing to do with water. That bright reflection might come from an exceptionally smooth patch of the terrain beneath the ice. Imagine a frozen lava plain, its surface polished by volcanic flows billions of years ago and preserved under ice. It reflects radio waves almost as well as liquid water does. Radar can't tell the difference. It just sees a bright spot and signals something here reflects really well. But whether that something is a lake or just rock, that's up to humans to decide. And humans often choose what they want to see. It's a familiar story. An indirect signal from deep below, impossible to touch or verify directly, followed by an interpretation that races ahead of the actual data. Seismic waves slowing down in the Earth's mantle? That's also an indirect signal, also an interpretation. The difference here is that on Mars, the mistake was caught because a second instrument was available to challenge the first. The story of the Martian lake raises a simple yet troubling question. How many of those bright spots on our radar images, seismic readings, and spectrograms actually represent something real? And how many are just smooth rock mistaken for water? Is there a way to tell for sure, without relying on indirect clues, but by holding something in our hands and studying it in a lab? There is a way to do this, and it has been waiting in sealed containers since the late 1960s. 382 kilograms of lunar soil brought back by 6 Apollo missions. Rocks that astronauts carefully placed into aluminum boxes on a dusty gray plain, unaware that half a century later, these samples would tell the story of a planet that no longer exists. The idea to compare the isotopic makeup of lunar and Earth rocks didn't come overnight. Back in 1975, William Hartmann and Donald Davis first proposed the giant impact hypothesis. At the time, it was just one of many guesses. Then, in the 1980s, Allison Cameron developed the first rough computer models of the collision. These early simulations showed that a giant impact could, in theory, eject enough material to form the moon. By the 2000s, models had become more precise, but the key evidence, chemical, remained unclear. If the moon formed from the debris of another celestial body, its composition should differ from Earth's. Yet it didn't. Or if it did, the difference was so subtle that only the latest generation of mass spectrometers could detect it, measuring fractions of a percent in the ratios of oxygen and titanium isotopes. And this is where the real mystery begins. If Theia came from the distant edges of the solar system, say beyond Jupiter's orbit, its isotopic signature should look completely different. Each region of the early solar system had its own unique chemical fingerprint, like dough baking on different shelves in a single oven. Closer to the heat, one composition. Farther away, another. Meteorites from Mars differ from Earth's rocks. Meteorites from the asteroid belt are distinct too. But lunar samples? They're almost indistinguishable from Earth's. A groundbreaking study published in the journal Science took this very paradox as its starting point. Researchers re-examined the isotopic makeup of samples from Earth and the Moon brought back by the Apollo missions. They then fed these findings into computer models, running thousands of simulations of planetary collisions with varying initial conditions, different impact angles, speeds, and origins of Theia. Each simulation produced its own prediction for the Moon's isotopic composition, but only one scenario matched reality. Theia didn't form out in deep space. It was born much closer to the Sun than Earth on a neighboring orbit, practically next door. That's why their isotopic fingerprints are nearly identical. Both planets grew from the same cloud of dust and gas within the same temperature zone. Theia wasn't some random interstellar projectile. It was Earth's neighbor. And here, we need to pause. We tend to think of collisions as disasters. A whole planet, about the size of Mars, slammed into the young Earth. The surface temperature soared to thousands of degrees. The mantle melted. Debris from both bodies blasted into orbit, where this fiery mess gradually came together over tens of millions of years to form the Moon. It sounds like the end of the world, but it was the end of one world and the birth of another. The collision changed Earth's mass and composition, shifting its orbit. But most importantly, it gave the planet a moon, a companion that stabilized its axis of rotation. Without the moon, Earth's tilt would wobble wildly, like Mars, which swings between 10 and 60 degrees over millions of years. On a planet like that, climate zones mix unpredictably. Seasons lose their rhythm. Glaciers advance and retreat without pattern. The moon acts like a gyroscope, a heavy flywheel that keeps a spinning top from toppling over. In simple terms, the impact that melted half the planet ended up creating the conditions necessary for life to thrive. Theia didn't vanish. It didn't evaporate into space or drift away. Part of it became the moon. Another part merged with Earth's mantle. Every time a volcano erupts magma from deep below, it carries atoms that belonged to another planet 4.5 billion years ago. We walk on Theia. We breathe its atoms. It became a part of us. Here's what's fascinating. We uncovered the secrets of our own planet's past because we could hold a sample in our hands, place it under a mass spectrometer, and read its chemical signature. But what do we do when the object of study lies so far away that it leaves no stones to pick up, sends no signals, and maybe doesn't emit any light of its own at all? The answer is simple. Instead of tracking light, we watch how an object pulls everything around it. We follow gravity. That's how we discovered more than 6,000 exoplanets, by spotting the tiny wobbles in their parent stars. 6,000 worlds. Gas giants, rocky super-Earths, planets where glass rains down. And yet, not a single confirmed moon. No exomoons at all. After 3 decades of searching, 0. It's like finding 6,000 houses in a strange city and not seeing a single car in any driveway. They're definitely there. They're just too small, too faint, or too close to their planets for our instruments to catch. And then a candidate appeared, but not where anyone expected. Around the star cataloged as HD 200 6893, astronomers found an object orbiting not the star itself, but its companion body, labeled HD 200 6893b. This object isn't a planet. It weighs about 28 times the mass of Jupiter. It's a brown dwarf, a failed star, too heavy to be a planet, yet too light to ignite nuclear fusion. How did they even find it? By using the same old trick. The Very Large Telescope, that's literally its name, detected periodic wobbles in a brown dwarf using the radial velocity method. It was swaying. Something invisible was pulling it back and forth, making it shift slightly closer to us, then farther away, in a steady rhythm. By measuring the amplitude of this wobble, they calculated the mass of the unseen object, about 40% the mass of Jupiter. A planet-sized object orbiting a brown dwarf. If confirmed, this would be the first exomoon, more precisely, the first confirmed moon orbiting a body beyond our solar system. But gravity doesn't just reveal moons. Sometimes it points to things that shouldn't even exist. Gravitational wave detectors are laser interferometers stretched over kilometers, shaped like the letter L, hidden deep in deserts and forests. They catch ripples in the very fabric of space-time, caused by collisions of monstrously massive objects billions of light-years away. In the year 2025, they recorded an event labeled S25-112 CM. 2 compact objects collided and merged. It sounds like a typical story, except for the mass of one of them. It turned out to be less than the mass of our Sun. More precisely, somewhere between 10 and 87% of the Sun's mass. And this is where the problem arises, one that defies easy explanation. Black holes form from the collapse of dying stars. When a star exhausts its fuel, its core shrinks under its own gravity. But the physics of this process sets a strict lower limit. For a collapse to go all the way and create a black hole, the core must have at least 3 times the mass of our Sun, not 2, not 1.5, 3. This isn't just an estimate or a rule of thumb. It's a direct consequence of fundamental equations that describe the pressure inside degenerate matter. Below 3 solar masses, the collapse halts, forming a neutron star instead. Now, imagine an object lighter than the Sun taking part in a merger as a compact body. It's like finding a fully grown adult standing just 4 inches tall. Not a dwarf, not a child. A full-grown adult with all the right proportions, bones, and organs, but only 4 inches tall. Biology simply doesn't allow that. In the same way, standard astrophysics rules out black holes with only half the mass of our Sun. There's no way for them to form. Stars just don't produce black holes that small. And yet, the detectors caught a gravitational wave. The signal is real, the mass is measured. So either our equations miss something fundamental about how stars collapse, or this object didn't come from a star. It didn't form from a collapse, not from any process we understand. If that's true, it raises a question. What era could it have come from, and what else might have formed the same way, remaining completely invisible to us? from a time when stars didn't exist at all. This might explain the unusual mass, and it's probably the most elegant solution. The object detected could be a primordial black hole, not a fragment of a dying star, but a relic from an entirely different era. In the first fractions of a second after the Big Bang, the universe was a seething broth of energy and matter. Temperatures soared into the trillions of degrees. Density exceeded even that inside an atomic nucleus. In certain pockets of this fiery mix, density grew so extreme that gravity crushed them directly. No star formation, no nuclear reactions, no millions of years of evolution. Just a clump of matter compressed into a point before the first fusion furnace ever ignited. Theorists call these primordial black holes. Until now, they have existed only in equations, elegant, consistent mathematics. But not a single observation has confirmed their existence despite decades of searching. Then, an object appears with a mass smaller than the Sun, one that couldn't have formed from any known star. If this is truly a primordial black hole, it stands as the first indirect proof that such objects exist. A relic nearly 14 billion years old, surviving the entire history of the cosmos, only revealing itself now through a collision with another compact object. But here's the intriguing part. If the early universe could create black holes without stars, what else might it have forged in the same way? Dark matter. It's a hypothetical form of matter that doesn't shine, doesn't reflect light, and doesn't emit anything across the entire electromagnetic spectrum. It interacts with normal matter only through gravity, pulling, bending, holding. And yet, it makes up about 85% of all the mass in the universe. 85. Everything we can actually see, stars, planets, glowing gas clouds, entire galaxies, makes up just the remaining 15%. Imagine a room with 20 people in it, but the light only touches 3. The other 17 stand in complete darkness. Their weight presses down on the floor, their mass bends the boards, yet not a single ray reaches them. This is where the real mystery begins. How do you catch something that's fundamentally invisible? One theory proposes a specific mechanism: WIMPs, weakly interacting massive particles. According to this hypothesis, dark matter consists of heavy particles that barely interact with anything, almost nothing, because when two WIMPs collide, they annihilate each other, mutually destroying themselves. At the moment of annihilation, they release gamma photons with a distinctive energy spectrum. In simpler terms, two invisible particles meet in the dark, and at the exact point of collision, a flash of light ignites for a split second, a tiny spark. Then darkness returns. Then another flash, and another. Each spark alone is insignificant, a statistical noise amid the roaring cosmos. But if you collect these flashes long enough, patiently enough, the sparks begin to form a pattern. The year was 2008. Scientists launched the Fermi Gamma Ray Telescope into Earth's orbit. Its detectors tuned into the highest energy photons, the very particles that, in theory, could emerge from the annihilation of dark matter particles. A new study analyzed 15 years of data from this instrument. 15 years of continuous observation focused on the region around the center of our galaxy. But the analysis deliberately left out the plane of the Milky Way. Too much interference comes from pulsars, supernova remnants, and binary star systems. All of it blinds the view, like oncoming headlights on a dark road when you're trying to spot a distant light on a hill beyond. 5,500 days, photon after photon. Algorithms peeled back each layer, removing everything that could be explained by standard astrophysics. That's a pulsar, gone. That's a distant blazar, gone. Cosmic rays interacting with interstellar gas, gone too. Layer by layer, they erased the familiar, like a restorer scraping away later additions from an ancient fresco, searching for the original beneath. Then, at one layer, something emerged, something that defied all known explanations. It's something spherical, perfectly symmetrical and smooth. Not stretched along the plane of the galaxy, like pulsars or supernova remnants behave. Not a pinpoint source, like a distant blazar. Instead, it's truly spherical, expanded in every direction from the center of the Milky Way, like an invisible bubble. A halo. It emits excess gamma radiation with energies around 20 billion electron volts. Each of these photons carries approximately 10 billion times more energy than a photon of visible light. This is not gentle infrared warmth, nor ultraviolet light. It's intense, high-energy radiation that shouldn't exist there in such amounts or in this form. Yet it does. Here's what's fascinating. For decades, theorists calculated what the signal from the annihilation of weakly interacting massive particles, particles of dark matter, should look like. They expected a very specific pattern, not a flat line and not random noise. Instead, a distinct bump with a peak in a certain energy range, tapering off smoothly on either side. They predicted a particular shape too, a spherical halo. That's because dark matter doesn't spin in a disk like stars do. It forms a three-dimensional cloud around the galaxy's center. The closer you get to the core, the denser it becomes. Higher density means more collisions. More collisions lead to a brighter glow. The detected signal matched those predictions. The energy spectrum matched. The spherical shape matched. The brightness distribution from center to edge matched. The theory, drafted long before the Fermi telescope even left Earth, fit the actual data like a stencil on a wall, line by line. But matching the theory is only half the story. The other half is ruling out everything else. And that's where the work begins. More like an investigation than pure physics. Pulsars? Millisecond pulsars do emit gamma photons, but their radiation aligns with the galactic plane, where old neutron stars are born and reside. The signal coming from the center of the galaxy is spherical. Pulsars can't explain that shape. What about supernova remnants? Their spectra don't match. They have different curve shapes and energy ranges. Could it be cosmic rays interacting with interstellar gas? That background has already been carefully subtracted, layer by layer, over 15 years of observations. What remains after all that doesn't fit any known astrophysical process. Not a single one. More precisely, none of the ones we know today. This is an important distinction, and the lead researcher states it clearly. Right now, no known astrophysical process can produce a signal with these exact properties. Dark matter annihilation remains the most likely explanation. Not the only possible one in theory, but the only explanation that fits the data, the geometry, and the spectrum we see. Imagine, just for a moment, that this really is the case. Imagine that the faint, spherical glow, 26,000 light-years away, marks the trail of particles shaping the very framework of the universe. Particles that hold galaxies together, preventing them from flying apart. Particles that steer the flow of visible matter, like riverbeds channel water. Particles that make up 27% of everything that exists, yet have never been captured by a single detector on Earth. Their only greeting comes as tiny flashes of gamma rays deep in the heart of the galaxy. A glow built photon by photon over 15 years. A glow that, in shape, spectrum, and geometry, matches exactly what theory predicted for decades. But one perfect match isn't a discovery. It's a footprint in the snow, pointing us in the right direction. Now the question isn't whether we see something unexplained. The question is whether this is enough to say, we have found it. Science is brutally honest. A match with a prediction doesn't prove anything. It's an invitation to test again, and again, and again, until there's no other way to explain the result. The gamma signal coming from the center of the galaxy matches the dark matter annihilation model in shape, spectrum, geometry. But matching the model is not a final discovery. It's indirect evidence that demands independent confirmation and further study, period. Without that confirmation, all the work loses its value. We've seen this before. The Martian lake in the Jezero crater looked so convincing based on mineral data that they sent a rover costing $2.5 billion there. The data matched the model. Geology said, there was water here. But then it turned out those minerals could have formed without a lake. The match fell apart. The model stayed just a model. This isn't failure, it's how science works. Failure happens when people declare a match as fact before testing it. Here's the key point. The Fermi telescope is the only instrument detecting this signal. One instrument, one team, one method for filtering out background noise. Until an independent detector with different optics, a separate orbit, and its own data processing algorithm confirms the same anomaly, we have to remain in the realm of probably, not definitely, not proven, probably. The next generation of gamma-ray telescopes will be able to test this. Ground-based Cherenkov arrays might provide cross-check data. Collider experiments could even directly catch a particle around 48 giga-electron volts. But all of that is still in the future, one that hasn't arrived yet. Let me share a thought, my friends. Impatience is the biggest enemy of good science. We want answers right now. We want 15 years of observations to settle the question once and for all. But honesty with the data matters more than speed, always. If a result is real, it will stand up to any test. If not, it's better to find out now than 20 years later. Now, let's take a step back for a moment and reflect on how far we've come. The year 709 before the Common Era. A Chinese astronomer records the coordinates of a solar eclipse. He's off by 8 kilometers, traveling dusty roads, without optics, without the math tools that won't appear for centuries. 8 kilometers. That's a distance you can walk in 2 hours. By 1609, Galileo pointed his 2-lens telescope at Jupiter and spotted 4 dots that shouldn't have been there. By 1933, Fritz Zwicky suggested that an invisible mass was holding galaxies together. By the 1970s, Vera Rubin proved this with her rotation curves. Fast forward to 2024, 15 years worth of photons, gathered one after another, formed a spherical halo of gamma radiation peaking at 20 giga-electron volts. 26,000 light-years from Earth. That's a distance light covers in a time span 3 times longer than all of human civilization's history. From an 8-kilometer margin of error on a country road to a radiation sphere half the size of our galaxy. That's what this species can do. Not the strongest, not the fastest, not the longest lived, but the only one to ask questions of the darkness between the stars and patiently wait for the answers. Every answer we've ever uncovered, from the isotopic nature of Theia to the shape of the galactic halo, never closed the book. Instead, it opened 3 new questions. We figured out what the lunar soil is made of, and discovered that the moon holds fragments of a world that no longer exists. We accounted for every known source of gamma radiation, and found a glow that has no name. Each mystery we solve only broadens the horizon of what we don't understand. No matter what the answer turns out to be, it reshapes the picture in both cases. If the signal is confirmed, we've caught our first glimpse of the universe's framework. If it isn't, then there's a process out there, one we don't even have a word for yet. Right now, as these words are spoken, the Fermi telescope keeps gathering photons, one by one, quietly, without fanfare. The data piles up. That horizon of ignorance keeps expanding. And maybe that's the best thing to say about us. We're not afraid that the horizon stretches on forever.